All right, so ladies and gentlemen, please listen. Here is what we are going to do today. First of all, we're going to check our work from Tuesday. So I'm going to come around and check you off that you have it done. I'll put an answer key up here in a moment. Then we are going to discuss the ideal gas law, Dalton's laws of partial pressure, and gas stoichiometry. We have finished with 25 minutes left at the end of each class that has been ability to start on working on the questions. And we have shortened this amount down from, we're doing the odd questions, hold on page 11, and then on 12 we're doing 1 through 3. So we have considerably shortened that. All right. The other thing that you have that is homework that you need to do for Monday is that there is a pre-lab for the gas law lab. Did that not save? For some reason I have 2 of them on here now.
I thought there was 3 before. Wait, they're different though. Well, yeah, they are different.
No. Oh, I did it last night, and then I did another one this morning. All right. So, please turn your voices off. There is a pre-lab here. You may watch the pre-lab and fill in the lab in your lab notebook, or you're free to just look at it. It is at the back page of the packet. And you are free to just draw your own instructions for it. Okay? So, but it needs to be done on Monday when you come in. If it's not, you won't get 2 points for that. That's 2 points you automatically lose. Okay? If you don't have it done in advance. All right, and you can follow along with the video that I made. I made that last night. You're welcome to follow along with that, or however you want to do it. So you will need your lab notebooks to go home, but you do not need the lab notebooks out in class right now. Okay? So what we are going to start with is check our work from Tuesday. So, and if you're wondering what the red and white lines are, I'm videotaping this because I've had several kids miss class today because of various things, so that they will have access to it. Because I'm nice like that. All right, so I'm going to walk around. Here's the first page. I answered all of them because it's fun. But I realize I only assigned you the odd ones. So those are the only ones you have to have answered. But if you're an overachiever like me and you went ahead and did them. And I'm going to come around and make sure that you have this done and mark you off. So.
I do not have it all done.
Oh, then you don't get points.
Yep.
You get points when you are done and turned in. Okay. Just because you don't have it done doesn't mean you can't still do it. You're still allowed to do it and turn it in. I'm just probably going to take 1 point off. For being late. How are you guys? Good job. Alright, not your fault.
I did this.
No.
I tried to.
I'm not okay. It's gonna be I'll keep playing.
Did you have yours done?
Yeah.
No? Okay.
Are you okay?
Oh, yeah.
Okay. I'm just alright. This is good. Okay. Not really. I'm lying.
So?
Just to be okay. Okay.
Okay. Anybody have any questions about this page?
No.
All right, the next page. Anybody have any questions about that page? Yes, Perry. I can. Sure. Anyone have questions about that?
Number 3, I did not think correct.
Did you change to Kelvin?
No, I didn't. Goodness gracious.
All right, the last page. Can I go on?
Yes.
Is anybody going to scream at me? The last page. Oh, no, first hour it was like, don't move. Don't you change that till I'm done. So there's Gay-Lussac and combined gas laws. And I actually did number 3 wrong on Gay-Lussac's law, and we fixed it first hour today.
So, we have a question. Did you get 323K
For what?
for number 3?
That's 2. Wait.
323.
323 Kelvin.
Yeah.
It was 50 degrees Celsius.
Oh, you're supposed to change that and then put it into there again? Okay.
You always change the temperature to Kelvin.
I have a question.
Yes.
For number 1 on the combined gas laws practice,
Uh-huh.
I just put 32,621.
That's fine.
Okay.
That's fine.
Did you just round to 33,000?
I use sig figs, but
Okay, got
third hour has decided that in their class at least they're always going to have 3 sig figs no matter what my problems have. So, and I was like, okay, fine. So.
Okay, so I set it up perfectly, and then I just.
Okay, nobody else have any questions?
Can you work out like number 1, please?
Number 1 on what?
Combined gas law. Yes.
Okay. 1. Good luck, Brooke. You're gonna cross multiply. Here, I'll pick a different color. You're gonna cross multiply. No, we're not using a tablet. 35,000 times 1.01 times 263 Kelvin is equal to V2 times 0.950 atmospheres times 300 Kelvin. Oh, I just changed the size of my... Why does technology hate me? I'm going to pause. What you would do is divide... You could, of course, work them out first. But that's ultimately what you would do. Those sides would cancel each other out.
Okay, how would you divide it by 0.95 and 300?
This times this times this divided by this times this.
Yes.
And did you say number?
And you put parentheses in there. Okay?
Did you say number 3 was wrong on the combined gas laws?
The 3.55 was wrong. 3.31 is the one that first hour corrected me to. Okay. Questions? All right. So today we're going to learn a new topic. Today we're going to learn a new topic about the the ideal gas law. So what you need to do is turn in your notes to this page. I think it's page, I've got it written down somewhere. Page 7. You're also going to need your mole map out. So go ahead and get your mole, it's page 6. You're going to need your mole map out. So go ahead and get your mole map. Okay. So, on Tuesday, we discussed the fact that you had 4 different things that could affect gases: pressure, volume, temperature, and number of moles. Those are all variables that can affect gases. And what we mainly did on Tuesday is take a look at one gas and change something about it and use the second set of circumstances to answer the question. So like we could, if we were doing Boyle's law, pressure 1 times volume 1, and we change pressure 2, that's going to cause volume 2 to change. If we know one of those 2, we could solve for the other one, right? Mm-hmm. So wouldn't it be nice if you had some kind of a standard? You guys know what standards are? Yeah. Standards are things that you compare to. For instance, today and tomorrow, the juniors are taking the state science assessment. That is a standardized test, and they use that data, so that they compare our scores to other scores, and our school improvement team uses those scores to say, oh, we're really bad in science this year, so we need to come up with a plan on ways to increase those. And to follow, to teach. So I have a set of standards that you all have to learn. Mine are much more loosey-goosey than the ones in English and math, but that's okay. So we have something standardized when it comes to gas laws. Scientists decided, and I don't know why they chose this, and I can't tell you when, although I know they refined the definition in 1980, that standard temperature, if you're dealing with gases, would be 0 degrees Celsius, because that's the freezing point of water. All right. Of course, we'll want Kelvin. So standard temperature is 273 degrees Kelvin. That would be better. Okay. And for terms of pressure, the average pressure on the Earth's surface at sea level is 1 atmosphere. So this is standard pressure, 1 atmosphere. So if you have a gas at 1 atmosphere and 273 degrees Kelvin, we can find some information out about it. And it just so happens, if you have 1 mole of a gas at STP, we abbreviate standard temperature and pressure, STP, 1 mole of a gas at STP has 22.4 liters. It doesn't matter what gas. It doesn't matter how heavy it is. 1 mole of carbon dioxide at standard temperature and pressure is going to occupy 11 2-liter bottles. 1 mole of hydrogen gas at standard temperature and pressure is going to occupy 11 2-liter bottles. Okay? This is something that's true. Okay? Now, remember I was talking about we had the before and the after. So if we put the combined gas laws up there, remember when we solved this one, we then changed some of the variables, and we were able to solve it in the new situation. Well, now we can plug our information for STP in here. Okay, so what is the pressure at STP? 1 atmosphere. So we can put in 1 atmosphere. What's my volume at STP of 1 mole of gas? 22.4 liters. My 1 mole is N2. And what is my temperature at STP? 273. So if we go through and do the math for that, we end up with a number 0.0. Why can't I think of it now? 802. 821. Thank you. I don't know why I just blanked that. 821, and it has really weird units. Liter atmospheres over mole Kelvin. We call this the ideal gas constant. So now we can say that 0.0821 is equal to a gas that has pressure 1, volume 1 divided by the number of moles and temperature. Okay? So you got to put that into the equation. Nobody wants to have an equation that has a number in it and letters. So we have named the ideal gas constant R. I don't know why. And if we put R, if we set PV over NT is equal to R, we can rearrange that algebraically and we get this. And this is what the ideal gas constant is universally known as. Pervnert. Pervnert.
Why does this class have the oddest name?
I know. Pervnert. I know my daughter called it that. Pervnert. So, ideal gas constant is equal to Pervnert, or is the R in Pervnert. Now, this is if you have atmospheres. If your ideal gas constant, if your pressure is in kilopascals, this would be your ideal gas constant. But for simplicity's sake, we're only going to use atmospheres. Okay? So you don't need to worry about that. Is this something you have to memorize?
No.
No, it will always be given to you. It's a constant. It will always be provided. Okay? All right. Now let's look at our mole map because we're going to use this information about the mole of gas at STP. So on your mole map in the top left-hand corner, you are going to write volume of a gas in liters. And above that, you're going to write at STP. If you are at STP, you know that 1 mole of gas will take up 22.4 liters, right? Mm-hmm. So draw an arrow from moles to volume, and you're going to multiply by 22.4 liters per mole. We call this the molar volume of a gas. And on Monday, we're going to do a lab. We're going to try to achieve a molar volume, the number for molar volume of a gas. We won't collect a mole of it. We'll collect a smaller part of it, but we should be able to still get the same ratio. If you know the volume and you want to change to moles, you divide by 22.4 liters per mole.
What happens if it's not at STP?
If it's not at STP, I'll show you in a minute. Okay? If it's not at STP, you have to use Pervnert. Yes.
So is STP just like the average of things?
STP is the standard temperature and pressure. And because we know that 1 mole of a gas, any gas, at 1 atmosphere and 273 degrees Kelvin will occupy 22.4 liters, we can substitute that in for any piece of information. Okay?
So they can say like in a word problem at STP.
Mm-hmm. Exactly. And Gavin's question about what if it's not an STP is very important, and I'll give you that here in a little bit. Okay, so you guys have any questions about PervNerd? Then let's put it into practice. So please, in your packet, flip back to the insert that has the bigger page numbers up at the top and find the little girl playing the trumpet. Find the little girl playing the trumpet. Okay? Now, once again, here we have the ideal gas constant. 0.821 liter atmospheres moles degree Kelvin. If you were using a system that had kilopascals for your pressure, your ideal gas constant would be 8.31. We just saw that on the other page. If you were using millimeters of mercury, your ideal gas constant would be 62.4. I think when I was in high school, I think we used kilopascals because that is the one I tend to remember. But I wouldn't even know that anymore if that's what I used in high school. So now we're going to solve some problems. Okay? It says, if I have 4 moles, what variable does 4 moles correspond to in PervNerd? N. At a pressure of 5.6 atmospheres, what variable is that? P. And a volume of 12 liters, what variable is that? V. What is the temperature? So we're going to solve for T. How do I get T by himself, algebraically? Divide both sides by N and R. So T is equal to P, not T, V over N R. So now you just plug it in. Where are we going to get the number for R? It's the ideal gas constant. But if I hadn't asked you that, somebody would have asked me that. So I was trying to preempt the question. So 5.6 atmospheres times 12 liters divided by 4 moles times 0.0821 liter atmospheres over moles Kelvin. Atmospheres cancel, liters cancel, moles cancel. We'll have an answer in Kelvin.
Wait, what was the last bit? Is that
this guy?
yes?
That's the ideal gas constant, 0.0821. So, punch it in your calculators. Everybody should have a calculator out working on this. Yep.
So how do we know it's going to be STP for 0.821?
It's not. How do we know it's. Ask me the question again.
Like, how did you know it's going to be 0.821 for the STP?
Because we're going to use P times V over N times T. So we use the pressure at STP for P. That was 1 atmosphere. We use the volume of 1 mole of gas, which is 22.4. We divide by 1 mole of gas, because that's how many moles we have if we have 22.4 liters. And the temperature at STP is 273 Kelvin. So by multiplying that out and then dividing the top by the bottom, we come up with 0.0821. Okay? If we were to add, instead of 1 atmosphere, if we were to change this to 101.3 kilopascals, we would get that value. If we were to change that to 760 millimeters of mercury, which is also equal to 1 atmosphere, we would get this value. Okay? We aren't going to worry about those. We're going to make life simple, and we're going to stay in atmospheres. Yes? Yes. Let me get... You got it? All right. Yes. Go ahead and go. Yes, ma'am.
Okay, I'm confused on... So why didn't we just use the 273 Kelvin instead of the 0.0821?
Because 0.0821 comes from putting those together. You could do that. Here. You could go 5.6 atm times 12 Kelvin is equal to 4 moles times R is PV over NT. So pressure is 1 atmosphere, 22.4 liters, 1 mole, and standard temperature is 273 Kelvin. You could put that in. See, that right here is replaced by this. Okay, those are the same thing. You could put all that information in and you'll get the same thing. You could also set it up so that you had PV over NT is equal to P2V2 N2 T2, and P2 would be 1 atmosphere, V2 would be 22.4, N2 would be 1 mole, T2 would be 273. And you could solve it that way. It's all going to come out to be the same. It's just rearranged. Okay?
Okay, thank you.
Harry.
So on the like 2 equations, like why do we do P2 over V2 and then there's P1 over V1?
In the other equations, because we aren't using all the variables, we're just isolating 2.
So in this one, the equation for the ideals of gas, the equation is P1 over V1 equals N1 over T1.
Uh-huh.
Okay.
Wait, so would the answer be 1.3 T?
One for what?
1.
For 1, the answer is 205 Kelvin.
They're 205.
Yeah, that's what I got.
That's what I got.
How do you know it's Kelvin?
Okay, I figured it out.
You did? Okay. How did you put it into a calculator? 5.6 times 12 divided by 4 times 0.0821.
That's exactly what
Did you use parentheses? That's the problem. If you do this and don't put parentheses in, please excuse my dear Aunt Sally is going to multiply it by that and then divide it by that. PEMDAS.
Put parentheses on the second side too.
You would have to have parentheses over here. You could also do 5.6 times 12 divided by 4 divided by 0.0821. That will give you the same thing. That's how I do it. But that upsets people.
So what's the answer again?
205 Kelvin.
205,000.
No, 205 K for Kelvin. And the question, how do you know it's Kelvin? Because our units are Kelvin.
Yeah.
And that's the only thing that doesn't cancel out. All right, question 2. If I have an unknown quantity of a gas at a pressure of 1.2 atmospheres, which variable is 1.2 atmosphere going to be? And a volume of 31 liters, which variable is that? And a temperature of 87 Celsius, which variable is that? What am I going to solve for? N. So I've got PV equals nRT, and now I'm solving for N. How am I going to get N by himself?
P over RT.
Divide RT by both sides, right?
Yeah.
So pressure is 1.2 atmospheres. Volume is 31 liters. R is 0.0821 liter atmospheres over mole Kelvin. Atmospheres cancels, liters cancels. And temperature of 87. Do I put 87 there? No.
Plus 273.
I have to convert, and so I get 360.
That's cool.
So no matter
Kelvin
what
cancels.
you're finding, you always put the 0.0821 for whatever you're finding.
For R.
Okay.
Yeah.
Well, if it's not 0.0821, will it tell you different?
It will always be 0.0821.
It will always be no matter what.
The gas constant, because in here. Now, otherwise, no, you'll have to read the pressure and figure out what you're supposed to be using.
Okay.
Okay? But I'm trying to keep it simple.
Yeah.
What's the answer? 1.26. That's what I got.
1.26 moles. Question number 3. What is the moles? What variable is that? 60 liters. What variable is that? Temperature of 400 Kelvin. What variable is that? T. So now we're solving for pressure. How do I get pressure by himself?
Divided by volume.
Divide both sides by volume. All right, so 3 moles times 0.0821 liter atmospheres over mole Kelvin times pressure, temperature 400 Kelvin.
Is that 1.0821?
That's a parentheses.
Oh, sorry.
I could do this in real fence too, if you want me to. All right, volume is 60 liters.
So how did you find the 0.821?
0.0821. If we were to use a 1 mole of gas at STP, we substitute those values in here. 1 mole of gas at STP, is 1 atmosphere. STP is 273 Kelvin. 1 mole of gas takes up 22.4 liters. So we can take a shortcut and substitute 0.0821 for that.
Or there's 400 Kelvin.
That is what the 400 Kelvin. This is 0.0821 right here. Okay, so 273 Kelvin's a part of that. So you're going to take number of moles, 0.0821, temperature. That's 400 Kelvin.
Okay.
This is just saying the exact same thing as P, and that should be PV over NT is equal to P2V2 over N2T2. You're just subbing all that information in, and we call this R instead of P2V2 N2T2. Yes, Grace?
How do we know which equation to use?
You're always using the same equation of PV equals nRT. All I'm doing is figuring out what I'm solving for and trying to isolate it algebraically. Okay? So here, it wants me to tell you pressure. So if I'm going to solve for pressure, I have to divide both sides by volume, right? So that's why I'm using nRT. If you would prefer, you can leave it and do P times 60 liters is equal to 3 times 0.0821 times 400. That will work just the same way. And solve it that way. Both of them will do the same. Whatever works for you is fine with me. All right. So, who's got an answer for me?
1.664 ATM.
Yes, it would be 2 sig figs, but like I said, Third Era has decided, for their class at least, they have voted that they will always have 3 sig figs because they don't like 2.
Oh, we can do that?
If you want to vote for it today,
Yeah,
Vote.
let's do that.
Yes, we vote.
all right, we'll go 3 sig figs.
Hey,
What is when I write a test, it'll always be 3 sig figs.
Thank you.
What is the third figure here?
4.
And we are solving for pressure, so our units are ATM. Okay? Number 4. 7.7 moles. Which variable is that?
N.
and
Pressure, 0.090 atmospheres, is P. Temperature is 56 Celsius. We're solving for volume. So again, I'm going to write my equation out. PV equals nRT. And I'm going to solve for volume. How can I get volume by himself?
Divided by pressure.
Divide both sides by pressure. Pressure cancels itself out. So then we'll take 7.7 moles times 0.0821 liter atmospheres over mole Kelvin times
329.
329. Why are you using 329 for a temperature?
Because you added 56 to 273.
Because it's 56 Celsius plus 273. You have to convert to Kelvin. And then our pressure is 0.090 atm.
What's our label going to be for this?
It's volume. So what's your label for volume? Liters.
I hope I got that.
We're going to do 3 sig figs.
How do you do 3?
I don't know. I haven't gotten it added yet. Times 329 divided by 0.090.
2,300.
That's what I got.
That would be 3 sig figs.
Oh, 1,000. Anyway. The decimal?
All right.
Probably, yeah, you missed a 0 in between.
Oh.
You're good. It's the same number though.
Okay. Questions about that?
No, that's easy.
All right. So, now we're going to talk about Dalton and Dalton's law of partial pressures. Okay? Dalton's law of partial pressures simply says all the parts add up to the whole.
Big brain.
So if I tell you I have a pressure of 2.0 atmospheres and that gas A, which is oxygen, has a pressure of 0.9 atmospheres, and gas B, which is water vapor, has a pressure of 1.3 atmospheres, and gas C, which is carbon dioxide, has a pressure of 0.5 atmospheres. What is the pressure going to be of my remaining gas, which we'll say is sulfur hexafluoride? Say again? 1.17. How did you get that? It's basically you 2.0 and you're going to subtract 0.9, 1.3, 0.13, and 0.5.
Why do we subtract it from the table?
Because it's a cumulative thing. All the pressures added together equal the total.
Oh, yeah.
All right? So it's kind of like if we have all the all the people that use he and him pronouns in here. All right, and then we have the she and her pronouns, and then we have the they and them pronouns. We add them all up to get the total number of people in the room, right?
Oh, you forgot the sexy beast.
Oh, all right, and all the sexy beasts. We add them all up to get the number of people in the room, right? Well, this is the same thing you're doing here.
As the people with the he, and all the others with the three pronouns.
Okay.
Yeah, no.
All right.
What did you say the answer was?
So, why do we need to do this? Well, if you go scuba diving, you would need to know that.
I wasn't done.
I would never do that.
Are you?
It's in your notes.
I will never scuba dive.
Why not? Are you kidding? I've never got scuba diving with sound. You have to do chemistry for scuba diving.
Like a little. If we did them in Kansas.
Oh, my mom did her final dive for scuba diving in Lake Wilson, out in central Kansas.
That must have been memorable, yeah.
Is that SH?
SF6.
That's just an example, right? I know.
Okay. Now, the reason we need to know this is for the lab we're going to do on Monday. Okay? What we are going to do Monday is we are going to use a eudiometer. This big tube is a eudiometer. We are going to fill it with water, and we're going to put a little bit of acid in it. And at this end, we're going to put a piece of magnesium ribbon and a stopper that has a hole in it. And we will fill this up with water, put our stopper in, and then we will turn it upside down and put it into a beaker of water. And the acid will mix with the water and eventually get to the magnesium and react, and the magnesium will replace the hydrogen and form hydrogen gas, and the hydrogen gas will collect up here. And as the gas collects, it's going to push the water out, so then the water might overflow the container. No laugh? All right,
Sorry, I didn't get it.
this is water.
Yeah.
The water's coming down and it overflowed the container.
Yeah, I knew that was water, but I didn't know you were making a joke.
Oh, well, I lose. Okay, so you're going to collect hydrogen gas up here. Okay? There's only one small problem.
Yes.
Water becomes a gas very easily, which is why if you spill water, it disappears. So, if this is the top of our tube, here's our hydrogen being produced, but we also have water vapor floating around in there with it. Okay? When we do our lab on Monday, we are going to try to prove that the molar volume of 1 mole of gas is 22.4 liters. So we need to know the pressure in here without the water vapor, because the water vapor is hitting the sides too. All right? So in order to do that, we're going to have to subtract out the water vapor. So let's say the room temperature is 25 degrees Celsius. And the room pressure is 770 millimeters of mercury. Because this is in millimeters. 770 minus 23.48 to get rid of the water will give me the pressure of the gas. So let's practice that. In your big packet, if you will please turn to page 14? 14. So for page 14, we're going to work some Dalton's laws of partial pressure now. Okay?
Okay.
The first question tells us that we're collecting helium gas over water at 28 degrees Celsius. What is the partial pressure of the helium given that barometric pressure in the room is 750 millimeters of mercury? Okay? So that's our total pressure. That's total pressure. The two gases in there are helium and water. And we know that the temperature is 28. So if you look at page 15, you get a data table. Of course, it's sideways on mine, and I'm not quite sure how to get it to turn. But if you follow the column down and find, because it was 28 degrees, correct?
Yes. And
go across, there is the pressure of the water in millimeters of mercury. If it was 28.2, then we would use this value. If it was 28.4, we would use this value. But we're just using 28.0. So 28 degrees, the pressure is 28.349. So I can go back here and add that in, 28.349 millimeters of mercury. Now, how do I solve for helium? Somebody tell me what you get.
721.651.
Say it again.
721.651.
721.651. If we did 3 sig figs, we'd say 722 millimeters of mercury.
Well, that's what huge significant division. I thought it was like 3 decimal places.
No, it's 3, because look how not precise that number is. 750 is not precise. That's why we use sig figs, because 28.349 is way precise, but our final number is not going to be that precise. Yes, sir.
So on the chart, you just look at the temperature and you just go through the 0.0 column for every single one?
Mm-hmm.
Okay.
Yeah. All right, question number 2. The primary components of air are carbon dioxide. So we have pressure of air is equal to the pressure of carbon dioxide plus the pressure of nitrogen plus the pressure of oxygen. In a sample at exactly 1 atm, that is the pressure of the air, the partial pressure of carbon dioxide is 0.27 atm. Nitrogen is 0.53 atm. So what is the pressure of my oxygen? 0.3? Okay. 0.2?
You're right, that's not there.
0.20 atmospheres. You see how we did that? The third one, we have a problem. Because what is our pressure given here? Atmospheres, right?
Yeah.
But our chart is in millimeters of mercury, which means we either have to change that to millimeters or we have to change millimeters to atmospheres. But I will tell you, those millimeters of mercury are so small, if you change them to atmospheres, you're going to have a really, really tiny number to subtract from 1.1. So I am going to change 1.1 to millimeters of mercury. 1.1 atmospheres. What is the relationship of millimeters of mercury to 1 atmosphere? Does anybody remember?
760 millimeters of mercury.
Very good. 760 millimeters of mercury are equal to 1 atmosphere. So if I multiply those together, what do I get?
336.
So this is the total pressure. That is going to be equal to the pressure of the water plus the pressure of the unknown gas. So what's my temperature? 35. So if I go to my data table and I come down here to 35 and I read sideways, what do I get? 41.175. So what is the final pressure of the gas?
1.1
Say again?
1.05 atmosphere.
Okay, but let's do in millimeters of mercury first.
795.
And then you could change that back to atmospheres if you wanted to. All right, we're going to take a quick break.